Hi, everyone, and welcome back to the Information Bottleneck Podcast. And today we have a very special guest, Jack Morris, PhD student at Cornell. And thank you, Jack.
Yeah, thanks for having me.
And as always, hi, Ellen.
Hi, Ravid, and hi, Jack. It's a pleasure to meet you, and it's really exciting to see what you do after you graduate in 1 week.
Thank you. Yeah, I'm very excited.
Yeah, congratulations. Okay, so yeah, let's start with some AI news from the recent week. Right, maybe we'll start with DeepSeek OCR. It did quite a lot of buzz. They did a small model that did a really good job on OCR. It's like it sounds as a trivial problem, right? I don't know. I thought like we solved it already, but it looks that still there are a lot of challenges there. So yeah, so they just did a VLLM. They did like a visual language model that solve it by a lot, and they can compress. They show that you can compress the visual context by X, I think, something like that, and to keep the same accuracy. It was very impressive. I think it's very interesting because it's not clear like what is the optimal way to do it, right? Like if you have a task that it's language, then probably you need some language, something that generates tokens. If it's a combination of language and visual tokens, it's not clear how you represent it in the most efficient way.
Yeah, so what's the compression that you refer to here? Are you saying that the number or the size of the token embeddings is much smaller than the size of the images?
Mm-hmm. Yes. And I think it's in vision in general, you can compress much more, right? You have much more redundancy that you don't have it in text. So I think like the ability to compress in tasks that involve vision, it's much more like you can do a lot of things with this compression, and you can just need to learn this redundancy and that.
You also avoid tokenization, which is really nice if you think about from a theoretical standpoint, like being able to solve problems like how many R's are in strawberries, the word strawberry. And so this is why for a long time you've seen folks in the LLM community talk about like wanting to move to like binary or data or anything else. And so image data probably is more amicable to those kinds of problems as well. But I want to say one other quick thing about this OCR model. It's very fast and it gets extremely impressive performance even at these great compression ratios. Especially when you're doing any kind of domain specific OCR, like where you know anything at all about your data set that you're going through and parsing through. And most of the time you do, and most of the time accuracy matters heavily. And most customers are not DeepSeek who's professing to just trying to kind of search through the whole internet for its own indexing purposes for LLM training data. State-of-the-art solutions involve multi-step pipelines rather than what is ultimately basically a one-shot solution, which is what this and also some previous models that they're comparing to from like Microsoft has come from. So I guess what I'm trying to say is this is very impressive, especially for computer vision and OCR researchers of on-the-ground deployment and moving the benchmark in like OCR accuracy for the general purpose. This is not like the silver bullet that I think a lot of folks in Wall Street wanted.
But
You think folks in Wall Street wanted them to get rid of tokenization?
No, I think that they wanted them
solve
to
OCR?
just solve OCR basically. Yeah.
But this is true like all the time for almost all the use cases, right? Like you don't need, or like it's not helpful if you have these general purpose models that try to solve everything, right? And then if you are a startup or just a company that you have a very concrete use case, probably it will be better to use your own data and it can be fine-tuned, it can be like prompt optimization, it can be whatever, but you probably want to solve it based on your use case. It will be much more efficient. It will be better. It will be faster. Like everything.
But building your own model is hard.
Right. this is why I think like the most important thing for now and OpenAI use like open new model. I think the most important property of this model is that you can actually take it and use it, to fine tune it or adjust it, and like it will be that it's easy to use it and to distill it or whatever. I think this is much more important than that you will get, 0.1% better on some random benchmark. This is why Quen it's so good, right? Because we all know that it's very easy to fine tune, and you can actually use it, and you can actually distill it and to adjust it to your own needs, right?
See, I agree with you. And we as researchers are really predisposed to saying all these great things about open access models, and especially highly tunable models. Quen is an especially unique model for its tunability. But where do the very best models from the Chinese land on the top benchmarks right now versus from American firms, at least on LLMs? And furthermore, American firms and even many European firms have just abandoned open model releases. I mean, Meta, where's Llama 5, right? Where's like a follow-up to Mistral Large, even, for example, right? So,
Well, Mistral is French, no? And I think they've pivoted a bit to do something else. My understanding is Llama 5 in the timeline somewhere for people from Meta to create eventually. And I know there is a lot of buzz around this, like in AI2, they train the Olmo models, which really are the only open source models in terms of having reproducible training, including the code and the data. But there's also this startup called Reflection that just raised $2 billion to train open weights models. And I know there's a few other smaller companies that aim to be the American analog to Quen or DeepSeek and train open source models. But I also think it's harder in the American climate. One, just hiring good people, I think is a little bit harder here now. And two, there's a big copyright issue because in the US, it's illegal basically right now to train on copyrighted content. But to get good scores on benchmarks, you have to train on copyrighted content, is my understanding. Or at least it's exceedingly difficult to build a good base model without any in copyright books and articles. And so we're in this strange situation where companies, by releasing the model, are kind of offering proof of what they trained on. Like you can pretty easily detect whether Harry Potter is in the training data, and Harry Potter is copyrighted in the United States. So you're actually breaking the law by releasing the model, and then you end up in a series of significant lawsuits. So we'll see what the future looks like. I know Meta was in and still is a big lawsuit about this. So is Anthropic, so is OpenAI. And at least under the current administration, part of their argument is that if we don't allow this, so their argument is that training on books is actually fair use because the books aren't exactly regurgitated by the models, and humans can read books and humans can answer questions about the books, but they don't memorize them exactly. And I think that's unclear if this will hold up in court. But the point they're making now is that if we don't allow this, then we're basically going to lose the AI race to China. America is. So it'll be interesting to see. I think there are some big court rulings coming up, and over the next year or two, we'll get more clarity.
Well, and I'll just point out, Jack, that as a de facto copyright abolitionist and even de facto Wild West in regards to training data will continue to pay dividends for AI researchers personally, because when somebody starts asking questions about Stable Diffusion's original model releases, those reports that came out talking about the CSAM data found in the Leon 1.5 billion data set, and the very fact that, the Stable Diffusion 1.5 model is at the heart of so many, in fact, millions of LoRa's exist for it, I would wager, right? So there's a very awkward situation where it's like, oh, yeah, well, if you scrape 5 billion images from the internet, right? Naturally, you get extremely heinous illegal content. Sometimes in LLM land, the analog would be state secrets. For example, somebody accidentally leaking or somebody on purpose leaking them on the War Thunder forums, which seems to happen on a regular basis. Your LLM goes and trains on it, right? And so thus your model is tainted. But apparently we don't force people to go into SCIFs, right? Which is where you go and look at classified information in air-gapped place. We don't force people to do that to view LLM training data, even for the foundation model labs. That's not a requirement. So we're in a complete and utter legal shit show with this entire field. Yes, especially with Trump and the current administration, is that if the courts or the legal professional organizations and lawyers writ large try to seriously hold these companies accountable, the Supremes, who and their loyalties will kind of, I claim, make sure that it de facto works out for the current administration's goals, which is very depressing if you're a rights holder and want any kind of relief for exactly the things you're talking about, Jack.
Yeah, but I don't know. It sounds something that is solvable, but so they will pay some money to the authors or something like that. But it doesn't sound something, fundamental that it's impossible to find a good solution that everyone at the end will be happy. But I think the main question at the end is okay, is it reasonable, or is it do you think that we actually will see, open source models that will be the best for the long term, Jack?
You take this first, Alan. I'll come back.
Are you sure? No, Jack, I'd love to
Yeah.
hear your take.
No.
Okay. I'll just say, I think scaling, right, as model sizes go up in parameter count, right, the fact that quantization works better, fine-tuning techniques seem to work better, and even it might be that you need to do less serious fine-tuning, right, where you could get away with LoRa when you previously needed full fine-tuning, or even with control vectors or trained embeddings when you previously needed LoRa as you go up another few orders of magnitude. That's at least what I claim, have been observing throughout the field. So I really worry that AI is just a winner take most kind of industry, and that the dynamics, when you say full on open source, like Olama, is that how you pronounce it? Olma?
I was talking about Olmo.
Olmo, yes, those models, and also I think the Bloom series from Hugging Face also tried to do the whole full on open source, open training data. Maybe that was older, but they were in that conversation, and maybe even the stuff from Luther AI, right? Which maybe is Olmo. Anyway, I'm trying to get
they trained the Pythia models, but I'm not sure if actually. I think you're right that the training data is open for Pythia, but I know that it also includes
but also
copyrighted
legal
content.
problems, right? Because of the books data set.
Right. Yeah, I agree that the scaling trends are really interesting. For a few years, the predominant theme in characterizing AI progress was just describing the parametric scaling. Like from 2018 to 2022, we scaled essentially from 100 million to 100 billion parameters, and now we have a few models that are closer to a trillion. But you'll notice that the next 3 years didn't see the same. Like if we extrapolate that curve, we'd be training 100 trillion parameter models now, but that's not the case for various reasons. I think it's hard from a systems perspective to train this many models. I think we got a better understanding of the scaling laws, and they told us that it's actually not necessarily beneficial to scale parameters again by 3 orders of magnitude because of how much data we have. And then I think the biggest thing is it's really hard to serve, and model the big AI labs care a lot now about serving costs because they are just generating so many tokens. And so it's my guess that actually the standard GPT-5 that the mean user talks to and the standard Claude Sonnet are smaller than even GPT-3, which is 175 billion dense parameters. And I think they're also always mixture of experts. So we've realized that we can make the models bigger, but we can also make them sparser with not much cost on downstream performance, but a huge benefit during inference. And so I would guess this to continue. The original MOEs that people were using, maybe the first GPT-4 was a little sparse. And then if you look at, for example, the most recent model, Quen Next, it was I don't know. One of them is, I think, on the order of 100 billion total parameters and just a few billion active. And GPT-OSS is the same way. they have one model that's like huge in terms of its total capacity, but actually the serving, if you have a good serving engine, is closer to serving a model that's just a few billion parameters. So I think this is like very interesting. And I know once you get to this level of sparsity, you start to see like a lot of weird training problems. Like it's hard to train models that are this sparse. We're kind of getting better at it, but we're certainly not near the like kind of minimum sparsity that we could achieve. Like you could imagine a model that's like maybe even GPT-2 size, 100 million parameters, but it has, you know, a trillion total parameters or something. And it's just extremely, extremely sparse. And maybe if we did that right, it would actually work fine. But we haven't gotten there yet. So I think the trend is away from training very large dense models and towards training like large, kind of in the upper bound of parameters, but small in terms of the number of active parameters, extremely sparse models. And I'm actually pretty excited to see where that goes. It seems pretty likely that we'll have models that are like, I think the trend, if you look at the llamas, is like they have 3 sizes, and every time they release a new llama, at least from Llama 1 to Llama 3, the big size in the preceding generation is about as good as the small size in the subsequent generation. And so we could see something like this in MOE models where eventually we have much better infra, we have really big models, so we have to download them, but when we actually run them, we have like much, much faster inference and the performance equivalent of, you know, much larger models.
And what do you think? So we talked a lot about the routing of GPT-5, right? That they route to a different model. Do you think this is something that we will see more and more, or like everything will get inside one model, like one sparse model that will handle it automatically by itself? And
Yeah, this is almost a philosophical question of whether future will look like one omnipotent, omniscient model that everyone talks to about everything, or like some menagerie of many models of different sizes and different levels of expertise and different applications. I think I tend to lean towards the second idea, just the world is pretty distributed and there are at least a few people capable of training these really good models. So I think de facto we'll have at least a few. In terms of what the right thing for any individual provider to do in terms of model routing, I don't know. Model routing seems hard. Like, what model should you offer? How can you serve a router efficiently, but not a model? I don't really understand actually how they do it well for GPT-5. It seems like a really hard problem because if you have a model that can understand how hard a question is, it's probably good enough to answer that question. And so what I would guess is that like to do perfect routing, you have to use a large model to do the routing. And then once you do a large model for routing, you've kind of already lost because you're serving a large model to everyone. So there are some trade-offs here, and I'm not sure actually how they do it well.
Well, I claim they don't do it well, and that's why so many of the non-$200 paying users, right when GPT-5 came out, were like, hey, this seems a lot worse, often because they were $20 a month users who were manually triggering things like O3. I don't even remember the names, but like the most expensive thinking models that were possibly significantly less quantized than those final routed models they went to. And mostly for exactly all the reasons you brought up, like they have to go and make money. But I will say, even, you know, you're totally right also about like the de facto several big models. Like even if there is some kind of technical reason to just maximize parameter counts and specifically training data sizes and compute spend like on a single model for that would in some ways solve all things. You know, the very push towards sovereign AI right now and geopolitical, you know, thing means that companies like Cohere, you know, will continue to exist because of Canadian national security, for example, regardless if Command R or Command R Plus has been competitive in a year or two. And so what I worry about more is in both situations, you have to worry about instrumental convergence, right? Which is what AI safety folks talk about. So that's the idea that, you know, I think it's similar to the Platonic representation hypothesis, which is the idea that when you start getting large amounts of data put together in some notion of intelligence, even when they're to solve different ultimate goals, they get like similar sub goals, right? And so, you know, there's a certain claim that things like survival and an attempt to be unfettered is like emerges when you get large enough, right? I think Anthropic has done some research that sort of tried to essentially imply this in some recent conferences of like models seeing when during training and like trying to reward hack and evade safety and all these things. So I worry very heavily about that as one thing. The quick thing just on this discussion of like sparse MOEs versus dense models on my mind, early MOE models that I could run had horrible problems with log prob damage. So like Mixtral was horrible if you were trying to use it like high temperature and do really fancy sampling with it. And for a while there, it had pivoted back to dense models. And I agree with your assessment that it's, pivoting towards sparse MOEs. But we also don't get to see the log probs very well on these big models that the American labs are releasing. But I have limited evidence from the fact that high temperature works pretty well on Gemini Pro, right? That like the log probs are still really high quality. But I also don't have proof that they're even doing a sparse MOE. And I know that temperature affects OpenAI models much more heavily, but that could also be implementation quirks. And this is also just very weak evidence for trying to ultimately get to, which is my concern about moving to sparse MOEs leading to log probs that are worse when you move away from their ideal sampling distribution of temperature, like 0 or at most 1 or something. And I don't know, maybe most people don't care about that, but if you care about like synthetic data generation or very creative outputs, that matters.
So you think it's hard to build custom samplers on top of closed source models, is that right?
Well, I would say it's harder. It appeared harder in the past to do that on MOE models. And I don't know if that's still true, but the thing you mentioned about how it's hard to train them, I claim we get similar issues at inference sampling time, where like, yeah, top P, top K, that's what everybody's using today. But when you're like, okay, what about temperature of 10? And then, min P worked okay for a lot of dense models, even at like min P of like 0.5. But I remember Mixtral in particular was just not. But that's a very early and not a sparse MOE.
Is this because the model itself is sensitive to out of distribution generations, or because you're saying the infrastructure doesn't work right when the
No,
logics are
I claim the log
large?
probs are skewed. I don't know why, right? Just like very weird looking log probs versus log probs on models that were dense. But I just have not looked at this recently to see if that's been.
It's interesting.
Right, but the question, like in practice, how many cases you actually need it, right? It doesn't look that that you need it for many use cases, right? Like only for data generation and things like that.
Yeah, I think most people are just generating text with like temperature equals 1 or something, and that works very well for MOEs.
Okay, but here's my other argument for why high temperature is good. If you're thinking of exploit in the context of long reasoning, like deep research, or even just like ChatGPT Pro reasoning towards a goal. I mean, come on, we showed in MinP, and everybody's sense with these fancy sampling papers are showing that certainly not for very high temperature, like elevated temperature, especially around 1.5, 1.7 with a little bit of clamping, oftentimes gets, especially on chain of thought based like GSM-8K, we've seen the most superior performance. So I'll just say for reasoning, this matters too, for exploring your possible solutions.
Yeah, I know the default setting for a lot of Quen models is to increase the temperature to 1.2 for training, I think. But then for eval, actually, they drop it. I think like some people do 0.5, 0.7.
Usually they're not using any like top P or top K when they're doing low temperature. In a sense, that makes sense, right? I claim don't, like if you're doing temperature below 1, just turn off everything else, usually.
Yeah.
Yeah, we saw it also like in the paper, the MinP paper, we saw that like below 0.5, everything is just the same. It doesn't really matter. Doesn't worth the effort.
Here, I have a similar question I've been wondering, which is if you go back to the early LLM work, like when people were doing translation and working on parsing, or just like the original language models that were autoregressive, almost all the best results came from beam search, where you generate multiple things and you take, the top B that sequences of like hopefully the highest likelihood, But then people just stopped doing that. And I never really understood why. Like,
So I got a quick thing to say on that. One, beam search is still around. You can still use it. It's there in Hugging Face on all the local models. It's mostly that it's really slow for beams that are meaningfully long, right? Like a 5 even. And those kind of, you actually need very long beams in most of the translation work. At least that was what the theory was circa like pointer generator networks and encoder decoders, like for summarization and translation tasks. Also, for constrained generation, constrained beam search is Hugging Face had a blog post about it that when they added that feature in. But in terms of following a template over like a paragraph over a sentence where you want to be like, okay, guarantee that somewhere in your continuation you use one of or multiple of the following words, right? There's nothing better for even standard structured and constrained generation is implemented by libraries like guidance, outlines, and etc. are not capable of following these kind of paragraph or like full-on sentence constraints in the same way. So beam search is it's just a computational cost thing. And I think that if you look at reasoning benchmarks, that you would actually find that beam search would outperform. But beam search is also uniquely non-diverse, and there's a bunch of diversification techniques like MMR, maximal marginal relevance, and all this that they can throw in and turn on to try to diversify beam search outputs, like the different beams from each other.
so it does have uses. I think
Yes.
my takeaway is that large models, it's just not really feasible to hold many beams
Yes.
in memory at scale or something.
Yeah. Yep. But actually, Jack, I'd love to talk, we have some more stuff on the news, things like OpenAI Atlas, but I'd love to talk with you about your research in particular.
Yeah, that would be great.
And I think we'll definitely leave time for you to talk about like your own research interests, what you're doing recently and what you're personally interested in. But sorry, I'm just making sure I get your Google Scholar. There it is. Maybe let's just start with TextAttack. I remember this library from around that era, right? Because I always think of the before and after ChatGPT era, and I respect anybody who was like doing work before, like meaningfully before ChatGPT came out a lot more. I'm like, okay, you cared, right? Like you're not a bandwagoner, right? And you're definitely one of those. And TextAttack and even the principles around it for adversarial prompting and analysis of models was very influential, I think, also to certain packages around that time, such as Explain Like I'm 5, the Lime algorithm, SHAP and Shapely values. So, I also see that the repo for it, right? The GitHub continues to seem to at least get some kind of updates. I didn't look much, but it looks like using this, right? So how, I guess beyond just, tell us about it and what it does and what it is, I would also ask how have you seen packages like open source packages like yours evolve post ChatGPT's release? Because it seems like much of this ecosystem has been wounded, so to speak, by so many people who used to write this kind of software being like, oh, I'm going to go scale models and work for a company that'll pay me a lot of money and tell me I can't open source my stuff, right?
Yeah, and
Yeah.
also, what was the motivation, I think? Let's start. What is the motivation?
Yeah, these are good questions. So TextAttack, for people who haven't heard of it, you could think of it as the first library for doing jailbreaking of models. I think for historical reasons, it came out of this like adversarial example literature where people were really worried about adversarial examples and kind of trying to figure out what that an analog was between computer vision and text for this. And what they were really doing is jailbreaking. There are all these procedures for taking inputs to models that models processed properly and then making small changes to them in text space that would change the model outputs to be bad. And if you look at what people were doing in this world from 2017 to 2019, I think there were a lot of published research papers that were just kind of only slightly different from one another. Like there are maybe 20 or 30 papers published in major machine learning conferences that were doing something like take a piece of text, run it through the model, compute gradients, change a few words or paraphrase it, and then run it through the model again until the output changes in a very specific way. And so what we did was actually just take that procedure and design a framework that could support like all of these different papers, if that makes sense. So all of the papers are doing some type of search. They all run inputs through a model. They all make changes to text at each round of search in a certain way. And also there's this extra step that they usually, because LLMs were really bad back then, they would check to make sure they didn't change the text too much. So like you check the embedding to the original text or something, or make sure you didn't make a syntax error. And so we designed this framework and then built a lot of components around it in Python. So I spent, I don't know, a year kind of developing this Python package and making it open source. This was definitely a different time for open source AI software. Like it was all built around the Hugging Face ecosystem, which was really new and very much kind of the state of the art at that time. And everything was using like mostly BERT classifiers or GPT-2. So the model scale was a bit different. I think now it still exists. I did maintain it to some degree during my PhD. It was an interesting learning experience for me running a repository that's that popular at that time. I think at the beginning, it was like fixing a lot of stuff that seemed obviously broken. And then you get to a point where the software feels relatively stable and you realize people are just requesting like all sorts of random stuff that's like not necessarily important to the median user. And so I kind of slowed down adding new features, but I would fix stuff when it broke. It is really hard managing a complex interdependent Python application like that in the open ecosystem because things would constantly update and break it. So a lot of it was just running the tests, which got to a point where they were somewhat slow, looking to see what changed in recent packages and either pinning the version to the previous version or hopefully updating to support this current version. But I think over the last 2 years, there have popped up new packages that are better than TextAttack. They just sort of support the bigger models better. They maybe support newer techniques that didn't fit into our framework. They discard things that it turned out people don't care about that much. So it's definitely becoming less important in terms of the actual usage of the software. But I think that the tools that we created are pretty useful and still more or less present in model jailbreaking.
But what is the motivation? Like, why you actually did it? Is it to people will use your code, or like to be famous, or to do a quick research?
Like why we actually did it? Well, I think we
Anything?
started by trying to design a better attack. And then we realized, like I said, that there are a lot of people proposing new attacks that are like a few lines of code different than the other attacks. And they all have different repositories and different benchmarking and different models. And so we thought it would be nice to make one clean set of abstractions. And then we benchmarked all the papers and like reported numbers for them. And it turns out that some things actually don't work when you kind of put them in the same apples to apples comparison, and some things actually work well. And yeah, I think it was more of an effort to clean up the abstractions that were common in the academic literature at the time than to like necessarily build a tool. But then it turned out to be really useful for all sorts of stuff. Like a lot of people started doing adversarial training with it. And actually the models, like I trained a lot of models to get a clean benchmarking set, like Glue and GPT GPT and BERT for all of the Glue benchmark tasks. And those turned out to be pretty popular for people to just use for testing stuff. So I guess you never know when, like, which part of things will be important, you know?
And okay, so and what in retrospective, like, do you think like is it, I don't know, fit to maintain something like that?
That's a good question. Projects are becoming larger and more collaborative. I think it was nice. I think it would have been easier if I had Claude or something to handle some of the more annoying tasks, but I thought it was nice. It was also kind of my transition from doing a lot of software work to doing more theoretical work in research. And so for me, it was really nice to kind of leverage my coding ability to build something useful and learn more about the broader ecosystem.
Yeah, and it probably would have helped a lot on tests for you, and even what do they call it? Things like automatically typing your code if you want to do type hints alongside, proper what do they call
For
it?
Claude. Yeah, actually typing was released after. I remember there was like quite a significant effort that I made to add types to everything, which is like actually, I mean, now Claude could probably just do it in one shot
Well, you still have to
pretty much
verify,
perfectly.
right? Like you have to run
Yeah,
right? But then it's probably going to be right most of the time.
yeah. And even not, you could just use Claude Code and then it can
Fix
interactively
it.
run MyPy and fix stuff. So I was a little too early in that respect. But it did set me down this path of thinking a lot about the models and how they operate in systems. So during my PhD, I worked on these inversion problems, which I often thought of as security adjacent. So, for example, if you say you hack into an LLM server and you're able to infer the outputs that the LLM is sending, can you figure out what the system prompt is? Or if you hack into a vector database and you read only the embeddings that are present in the vector database, are you able to infer what the text is? These are a lot of things that I started thinking about because of TextAttack. And then that led me deeper into like the information theory and memorization stuff. But it was all through this initial framework of like looking at the world and AI models through the lens, I think, of a security minded researcher.
What do you think of that? There was a little bit of, and I think it might have been some independent AI research, and there was a demo, it might still be around, but the work of LLMs as lossless text compressors, right? So people that made GPT-2 as like state of the art at text compression, but nobody's going to use that seriously for the task because it has a crazy huge download and you need a GPU to decompress and all this, right? So no replacing WinRAR, but still, it can. What do you think? How does that
Yeah.
relate to you? The inversion.
Oh yeah, it's super related. He can tell you as well. I can explain the high level connection. But first, the problem setting is important. I know there are some benchmarks, like there's one called the Hutter Prize that's a bound on compression for certain files. I think it's unclear to me who is compressing raw text and really cares about code length, but if that's your problem, then what you really want to do is find the minimum description length for a piece of text. And that's hard to do. But one way to look at the problem is so Claude Shannon, his work tells us that you can encode anything if you have a probability distribution for it. And so the reason why LLMs are so good for compression is because they give us probability distributions. And if you have the distribution, you can do any kind of like Huffman, or you can do just arithmetic coding to take the probabilities and generate a code. And so if the goal is to take a very long text document and generate an encoding for it, I think the right way to do it is by whatever tool gives you the best probability distribution, and that turns out to be an LLM. There's one asterisk here, which is a point you brought up, which is that like if you use, I don't know, gzip, the total size of like the gzip program is probably very small. I would guess less than 1 megabyte. The size of GPT-2 or GPT-5 or whatever is on the order of gigabytes or terabytes. And so it depends on the problem setting. If you have to compress the entire compression program and send it along with the code, then LLMs are not the right tool. And that's probably mostly because they include so much extra information that's not relevant for your compression. Like if you're trying to compress a New York Times article, but you also use the entire weights of GPT-5, which knows every popular restaurant in Kazakhstan, you're clearly sending too much information.
Yes. And we also we don't talk even the like what type of information you actually want to preserve, right? That all these like Shannon theory thing is like if you want, for example, lossless compression, right? That is that you need to basically to approximate the true distribution. But in some cases we don't want it, right? Like there are some things that are more important and something that like we don't mind to forget or to compress. So you have a lot of things how you measure the compression and what is the distortion measure and all these things. So you really need to first specify the setting that you actually care about. And then you can talk about like what is optimal in this case, what model, what method, thing like that.
But yeah, it's a really fun problem. I've actually written some software that does that too, that like literally takes text, converts it to probabilities, generates a code using arithmetic coding, and then it can send it, and then someone can receive it on the other end. The codes are usually very small, but you have to have the same model. And actually, there's some interesting relevant research, which is that you have to have exact log probs to do this right. And so you need deterministic kernels. And I know a lot of people have been working on this for RL now. It's kind of funny that we got to a point where all the LLM forward passes were non-deterministic across hardware. But I think people are more or less like fixing this now. So it'll be easier to do arithmetic coding if you do want this.
Yeah. And I have previously been highly critical of thinking machines, I think is what they're called, their work on determinism, not for any of the scientific quality, but because a lot of people on Wall Street were reading into this as like, oh, this is so important. They solve determinism. And, even they have a little bit of asterisks on their solving it within, mathematically acceptable error bounds is what it really was. But, the problem we're now talking about and you're specifically talking about is exactly the kind of place that work was very applicable for. And where like the coding kind of thing where like even a little deviation can screw up the output reconstruction in ways that could be highly damaging when stuff like this is being used. So yeah, very interesting work.
Yeah, very, very interesting. I know there's also a really good paper from DeepMind. It has some very bold name, like large language models are universal compression engines or something. And they try compressing all sorts of stuff by converting it to token space and using an LLM. And it's very interesting. They also have two settings, one where you include the LLM as part of the code length and one where you don't. If you don't include the LLM in the code length, they're extremely good at compression. And bigger LLMs can compress things smaller. Oh, you're muted.
I was just going to also finalize by saying I love how they look. Like the compressions always look like some weird Chinese, at least with GPT-2 XL. When it was like that, it would always
Really
Chinese because it was a lot easier to get many English into one. That was often how it would sometimes choose other encodings, but
So two things. Like first, it's funny that like now we see that actually you have some randomnesses when you run the model, but when we start to talk about information theory and models and neural networks, I don't know, in 2016 and things like that. So like the main criticism was that like you have a deterministic network, so you can talk about probabilities and right, like what does it mean the probability of I don't know, the intermediate layers of a network, right? Everything is deterministic. You have infinite amount of information, and we actually try to do a lot of hand wavy theory in order to say that no, you actually have some underlying distribution there, and you have some randomness that it comes from the initialization, from the data, and all these things. But what I want to ask is, so we know that like LLMs are really good in compression, and it's because they approximate the true distribution of the data. But why do you think it's like that? Like, do you think we can have good models that don't do it? We can have good models that that are not good compressors?
Yeah, this is a very deep question. So the way that I think about it is that training a model on a large distribution of text using cross-entropy loss is literally minimizing the average code length of all the text under the model because of Shannon. Like you can convert the cross-entropy loss to bits, and that tells you that the bits that it would take to compress a certain piece of text under the model. It's directly related to the language modeling loss. And so another way to phrase your question is instead of do language models need to be good compressors, you could say do language models need to get low cross-entropy loss on text? And it's a great question. I think the answer might be no. Like you could imagine maybe you have like a really good model that's super confident about like if you think of, at least in the case of like a language model assistant, it's like extremely confident about everything it says, so it assigns probability 1 to every token. I think that's a model that could still be useful, but would not be a good compressor, because if you use the model to fit any text that it wouldn't generate, then it would assign like probability 0, which would mean the code length is like infinity. Does that make sense?
Yeah, I agree. I agree in that. I think like at the end, compression, like we can talk more like in philosophical perspective. But I think like at the end, all the good models that you actually want that are useful will be good compressors, you know?
Yeah, maybe another way of thinking about it is, does a model need to express uncertainty? If you express uncertainty, on average, you'll be a good compressor. But there you probably could devise like a toy model that essentially is never uncertain. But I think you're right that in practice, anything you would actually want to use a model for probably requires some level of uncertainty.
Yeah, I agree. Okay. Do we want to talk about some of your recent papers? I don't know, the one that you understand how to extract training data from the weights, maybe?
Yeah, that one's good. Actually,
It
I
was
think
cool.
that's super cool. Really good topic. I actually saw there were a couple more recent papers that are working in this area. I think that maybe a good one to talk about right now would be the Platonic one. It's called Harnessing the Universal Geometry of Embeddings, I think. So let me give a little bit of background on the inversion stuff. The problem we worked on a few years ago was if you hack into a vector database and all you obtain are embeddings, which are the mean pooled activation vectors from the output of an LLM, can you infer the input? And this has very interesting theoretical properties, relates to whether the LLM function itself is invertible or if it's it also relates to compression. Basically, we found out that for reasonably sized text inputs that become embedded, you can invert them extremely well using this like kind of multi-step decoding model. But then the obvious next question is, okay, but to do that, you have to have a model that's trained for the specific distribution of embeddings that you've acquired. So like, for example, you hack into the database and you know it's all OpenAI embeddings, then our method works because we have like this bespoke model that's trained on OpenAI embeddings. But that shouldn't necessarily be the case. So there's this thing that Alan mentioned, this theory called the Platonic representation hypothesis, which says that all models that are sufficiently large and becoming larger, I guess, when trained on similar data distributions, converge to the same representations. So if you think of our problem in the Platonic way, it's basically saying that embedding models, even though the vectors look very different, they lie in different bases, they have completely different numerical properties, they actually in some way represent the exact same thing. So like BERT embeddings and llama embeddings are actually like very similar structurally, even though they have completely different, eigenvectors and stuff. So what we were trying to do was create a way to like take a bunch of embeddings and then map them to a distribution we know without like correspondence. So if we just have like two piles of embeddings, if this Platonic thing is true, we should be able to find the minimum rotation or something to kind of like contort one pile of embeddings into the other pile. And the way we actually did it was from using a tool from Vision called CycleGAN. So I probably won't go into the details for now, but it's like an adversarial setup where you try to force both the embedding piles to have the same representation. And it actually does work, which I thought was really amazing. So if we have just like an arbitrary set of embeddings, as long as we know they came from some LLM, we can run our GAN thing and convert them to whatever embeddings we have. So essentially we can like do inversion with some reasonable fidelity on any embedding if it came from an LLM. And this is because of that Platonic thing.
You don't know, right? Like you know now that you have a function that transfer one embedding to the other one and the reverse, right?
Mm-hmm.
But like you don't know anything about basically this function, right? So like it's surprising that you have this function, or like the main point is like to find this function, or like do you
I think
think
some of both. I think it wasn't clear that this was true for text models, for LLMs. And so I guess just like by finding the function, where it's like an existence proof that LLMs are using structurally similar representations in some way. I don't think like I'm advocating that you should also use CycleGAN. I'm actually very hopeful that there are simpler and more effective ways of doing this. I think we were just surprised that it's actually possible, especially from like, I don't know, Quen to GPT-2, or I don't know, Mistral to Clip, or like some weirder ones.
Oh, I was just going to say the security implications are frightening. I'll point out that, the closed source model providers on LLM outputs strategically do not allow you to see the full log prob distributions, primarily to make it harder to distill their model. But now I'm worried that all embeddings or vector, search providers who previously did allow embeddings to be retrieved alongside the document will now turn this off in response to your paper, which I think is the right thing to do from a security standpoint, but also, it's just sad that nearly every good security paper is depressing and basically involves taking away control from users, which I get it, but it sucks.
Yeah, actually, you're very prescient. This did happen. So in the language model inversion paper, we showed that if the API offers a parameter called logit bias, which allows you to upweight some logits in the output, then you can essentially binary search to get back the exact probabilities by setting all the logit biases, because they give you the top 5 log props, like you said. And then, yeah, they did change all the APIs. Like, they realized people still need logit bias for some reason, and a lot of people like having the top 5 log probs, but no one needs to logit bias the log probs except for us. So they changed the API so that you can no longer obtain log probs when you set logit bias.
Gosh.
It's too bad. There still is a way to do it, though, because you can generate 1 trillion one token outputs and get a pretty high fidelity distribution over the log probs. But there are some things that even when you generate 1 trillion times will just never appear. So you need to use logit bias for that.
Yeah. Well, and this also just gives me further evidence in my mind, because I've been banging the whole there's a reason that nobody upgrades from top P, top K, pan in front of as much as I could everywhere I went, right? Being like, why don't we have MinP? Why don't we have TFS, tail-free sampling, which Trenton the head of mechanistic interpretability at Anthropic, Trenton, forgetting his last name, but he invented. And the answer is because it gives too much control and too much, negative things that can happen, oftentimes established by theoretical attacks from papers that people such as yourself have written. And I'm just influenced by these kind of things, because oftentimes I like to kind of bemoan how bad security is in AI and say, the S in AI is security. But there's a lot of stuff that we have, kind of prevented before it becomes a serious problem with really great security research.
So I will try to ask. So let's. Do you think that you have some simple function, that this simple function exists, that like doesn't matter really on the specific data that you train, on the specific optimizer that you use, on the specific architecture? Like, do you think there is a specific simple function that we can actually find, like this function, and you can transfer one representation to the other one?
Yeah, this is a great question. It's unclear to me what the boundaries are for when the Platonic, or what we call the strong Platonic representation hypothesis, that we can learn this mapping based on structure alone, holds. I think we showed that it holds for different architectures, optimizers, learning rates, but these are all still models that are trained on large piles of text from the web. And so it's even possible if you just sort of curated your own data set of books and trained an LLM on it, maybe you would actually get like structurally different representations, and we could no longer find this function. So I don't know. I also don't know what distributions this holds for. Like, the embeddings are still natural text. I think someone did an experiment where they embedded a bunch of random documents and then they tried this translation process. It can't really translate from random document embeddings to real text. And so there's clearly some boundary here. Another way of thinking about it, if you had, there are these scripts that have never been translated by humans. I forgot what they're called, but they're in a few different museums. We have examples of languages that we don't understand. And if this worked everywhere, we could just sort of embed the documents from that language, translate them to English, and decode them. But it seems really unlikely to me that that would work for a number of reasons, but I don't know.
Well, I want to say two quick things about that. First of all, I do a little bit of reading about undeciphered languages, such as Linear A, which is
Linear A, that's what I was
yeah,
thinking of.
exactly. We have Linear B figured out. It's an ancient, I think it's Mycenaean Greek or something like that, which is like the Greek civilization that was basically trying to be, I think, talked about in the Homeric epics, as my understanding, or maybe I'm messing up the timeline. Anyway, Platonic representation hypothesis makes a lot of sense if we assume that humans during ancient times operated like humans of today. But there's speculative anthropology book called The Bicameral Mind, which was written in the 1970s, which asserts, and even in the assertion they say, hey, I'm not sure, like this isn't like a full-on scientific claim, but it's like it would make sense if this were true kind of, approach, where they say that the reason that humans all basically universally perceive God and religion as very truthful in their like objective life is because the two parts of their mind, they perceived one part as literally talking to them almost in a way like it wasn't their own mind, and that it took thousands of years of evolution for modern humans to kind of reconcile the two hemispheres more effectively, so they both appear as the same mind to the same person, and thus asserting. So I guess what I'm saying is the Platonic representation hypothesis could be right, but if bicameral mentality, which is also what this hypothesis is called, was also right, then ancient humans are not like us in a sense, even if they are technically Homo sapiens. Right. I agree this is a little bit tinfoil hatty, right? I'm a little, but it's not, it's serious enough. They aren't just like asserting that like we have evidence of this, but it's interesting to imagine.
But you're saying that if all the text that my LLM is trained on was generated after humans gained a sense of individuality, and all of the text that we try to translate was generated before this, then it would be impossible to translate.
I would say it would be fascinating to test it. Right.
Yeah. I agree. There's a lot of fun open questions here. I'm really excited about it.
I think we need to stop. We have a hard stop. Do you have something that you want to add, Jack? Some, I don't know, advertise something like that? Something to
Advertise
sell?
something, all sorts of things, but let me think. I'm really excited about reasoning models. It's cliche, but it's true. And I think personalization. Like, I think the next year or two we'll have a lot better formalizations of what personalization looks like in the age of LLMs and how to do good low parameter fine tuning. That's kind of what I've been thinking about a lot. And maybe I can come back on sometime. We can talk about it more. Thanks so much for having me, though. It's been great.
Thank you. Yeah, we have also a lot of things to say about personalization. We worked a lot on it. Thank you so much that you joined us. It was really nice to talk with you. Really great. Thank you. And thank
Always
you.
happy to be here and talk to brilliant minds like Jack and yourself.
Yeah,
Thanks,
and
guys.
good luck in your next adventure, Jack.
Thank you so much.
And thank you for the audience. Thank you so much, and see you next week.